Alright, welcome back to day 8 of LeetCode grind. Solve or go home. 30 minutes solve or go home. Alright, let's see what we got today. Longest increasing path. Oh no, this does not sound fun. Okay. Alright, given mx matrix, okay, return the length of the longest increasing path in matrix. From each cell you can move in 4 directions, left, right, up, or down. You may not move diagonally or outside boundaries. Okay. Okay. I mean, the question is pretty clear. It's just the algorithm. Okay. Yeah. Has to increase. Looks. Okay, so first off, if you want to do min max, you'd be looking at like dynamic programming probably.
Okay.
Yeah, and that means I'm dead because I'm really bad at that. Okay, so we want to memorize the paths, and we want to recursively call this until we get the good stuff. But yeah, I have no idea.
No, I think you have an idea, but so I guess the first thing here is, let's say you know that in example one, right?
Yeah.
You know that nine. Let's say you start with nine. Right?
Okay. Sure.
What's the
You
longest
mean
increasing?
the index 009?
Sure.
Okay.
What's the longest increasing path from nine?
Nothing.
From 0, 0.
Yeah. Nothing.
It's nothing, right? It's itself, right?
Yeah.
Right. So in this path of 1, 2, 6, 9, right? When you're at 6, then what is the longest path from 6? From 1, 0.
Oh, if you start at 6, it's just 6 to 9.
Right. But when you're at let's say you choose to process it in such a way that by the time you get to 6, you know what nine's number is.
What do you mean by nine's number? Oh, you mean the
Mm.
the path that 9 gets? The you mean the output the sequence that 9 has, right? Like 9 is only itself, so it's only one.
All right. So actually, I guess before we go down this path, like you can imagine that you can just start at every location, right?
Yes.
And
Yeah.
then you just do the calculation and then run until it reaches the end,
Yeah.
and then you're done, right?
Yes.
But this is probably not optimal because you're probably going to have to recalculate many things over and over.
So what I think I get what you're saying. You're saying that as we build these, we're storing each square's longest path. So when we access that square, we know how much longer, and we just add it to the result instead of looping.
Kind of. So you're correct that we should be storing something, but there's a certain way that you can process things such that you never have to worry that the thing that uh, you're accessing at this point is like, I don't know how do I phrase this. There's a way to process this such that like you know that everything that you calculated previously is as high as possible,
Okay.
right?
Mm-hmm.
Because let's say you process nine, then you process nine, then you process four, right?
Yeah.
Um, then when you're at four, you don't know if you process five, six, or seven, or eight, right? And those can be possible next things, right? Like the eight below could be the a valid path from four, right?
Yeah.
So is there a way you can order this such that you only process things uh, once?
Okay. So, what about starting from the lowest index, the lowest number, not the index?
Right? You start from the lowest number, which is one,
Yeah. So you
and
find the ones, and then you do those. Okay,
right? So one is
okay,
empty.
so you loop through the matrix and then you build like a list or like a tuple kind of like the index that it's stored at, and then you sort it by lowest number, and then
Mhm.
you just build the paths starting from lowest number from left to right. From
Okay, so in the lowest number, it would be one, right?
Yeah.
So what is the value for one? It's gonna
So
be
there's two ones here, right? So
sure.
this one would be four. The other one would be, I think it can't go. It would just go 1/8, and that's it. So it's two.
No, so if you look at the one in position 2, 1, right?
2, 1. Yep.
Right.
Wait, is it two
What is
comma one?
this?
This is 2, 1. This one?
It's row 3, element 2, so it's 2, 1. Oh, that's 2,
No,
2.
that's 2, 2,
Okay.
right? Yeah. Okay.
Yes.
Okay. Yeah. If I'm looking at that, what were you saying?
And if you do your algorithm, how are you gonna figure out the longest path from there?
So,
Just walk through that example.
okay. All right. So you would check up, and then you can go up. So then that's valid. And you check left, that's not valid. So then you can only go up. So
Right. So then it's 2, right?
yeah. So it's two so far.
that one is 2.
Well,
Okay. And then what about the other one?
oh, I see what you mean. So this one would go here, and you can go here, and you can also go here.
Oh no, you cannot go there
Wait, what do you mean?
because it's not. It has to be strictly bigger.
Yeah, one can go to 6, right?
Yeah, this one can go to 6. That's right.
Oh yeah. Wait, you're talking about this one, right? This one, or are you talking about this one still? You're still talking about 2, 2, or are you talking about 2, 1? Which one are you talking about?
2, 1.
Yeah, so this one, yeah. So this one has two options. You can go left or up.
It was stream delay or something. What you're saying and what I'm seeing is slightly different.
Stream's probably delayed. Yeah. Here, hold on. I just put it.
Okay.
I'll put it
Okay,
on
okay.
Discord.
No worries. No worries. It's fine. It's fine.
Okay.
Okay. So start at 2, 1. You have 3 things to check. You have to check left, up, and right.
Yes.
Correct.
Yep. Yep.
Right is not possible because it's the same size.
Yeah.
Left is possible. Up is possible.
Yeah.
Right.
Mm-hmm.
So at this point, you still have no idea what the
Yeah.
answer is.
Yeah. You don't know, but you know
Because
you have two possible
Correct.
paths.
Right. So then for you to evaluate it, you have to go check the left path. It's like okay, 2, and then from there you check the up path, and
Yeah.
then etc. Right. Eventually you'll get to 1, 2, 6, 9.
Yes. Mm-hmm.
But what I'm saying is, and you know that'll work. That'll work. But then you run into the issue of calculating the same thing multiple times, right?
Yeah. Yeah.
So
For sure. Mm-hmm.
so what happens if you know the answer to what something is already before you even you know check it, right?
Yeah. That's magic.
It's not quite magic.
No, it's
So let's
DP,
say
right? So you're just memorizing basically. If you solve the path, you can
right,
store
right,
it.
right. So memorization is definitely something you want to do.
Mm-hmm.
But I'm saying, is there a certain order that you can do this in such that you never have to recalculate?
Never have to recalculate. So, never. Is that even possible?
Let's say you start with the 9s, right?
Okay.
And you know that 9 is the biggest number,
Yes.
and you just, there's no additional way to build from there, so it's always 1,
Yeah, they're both ones. Yep.
right? Then the next biggest is what 8,
8. Yeah.
right? So basically, if 8 was connected to a 9, then it would be like, oh, I know that 9 is 1, so 8 is going to be
2.
like 2, right?
Yeah.
If it was connected to a 9.
Yeah, but it's not.
Right. And then let's say you have a 7 somewhere, right? And it's like, oh, okay, I know the 7 it was connected to a 9 maybe, or some 7 was connected to an 8. But at that point, you already calculated 9 and 8,
Yeah.
so you know what those numbers should be,
Mm-hmm.
right? And then 6 and 5 and 4 all the way down to the lowest, right?
Sure. Okay.
So I'm saying if you do the processing of your matrix in reverse order,
Then
by
you
value.
then you can tell for sure that
then you know what the correct number is from that coordinate, right?
Because if it's the largest downward, then you know that it can't increase in size. It's the source of truth, right? Basically.
Oh, so that means let's say you process 9 first,
Yeah.
then you process the 6, and then you know that the 6 points to 0 is 0,
Uh-huh.
and you know that 0 0 is 1.
Yeah. So that means
And 6
is
just
2.
depends to that.
6 is at
right?
least.
So
Yeah.
you know that 6 at 1 0 is 2.
Yeah.
And then when you go to 2 0,
Yeah.
you know that it's gonna be the max value from the 6 before at
Yes.
1 0
Mm-hmm.
plus 1, right?
Mm-hmm.
And same with the 2 comma 1.
Yeah. Mm-hmm.
So then how do we get this ordering where we have highest value to lowest value and each coordinate?
Well, wouldn't you just loop through the matrix and then store the positionings and just sort it in reverse, and then that's where you start to build your path?
Yeah, that's definitely one way to do it.
Is that like inefficient?
Not quite. But there is a data structure that you can use. It's called a heap.
Heap.
Yes. And,
Okay, but then if you're using a heap, you still have to loop through it to store into the heap, right?
Yeah. So you loop through the matrix once.
Yeah.
And then
So
at
either way,
time,
you're gonna have to loop through the matrix. Yeah, it's just if you're using a heap, it's better because it's all one get for the largest element. But then I think what I was thinking about, if I was storing it as a tuple kind of thing, and it's just because then if you calling a sorting on it, it does have runtime. But then when you heapify,
So
doesn't that
store-
also have runtime as well?
Sorry.
When the heap heapifies to auto sort itself back into position, it still does a n log n to sort itself, right?
That's correct.
So it's essentially
so-
the same thing. It's just the heap is cleaner because you don't have to handle all that yourself.
Right. So heap pushing is log n, right? And you have to do it n times, so it becomes n log n.
Yeah.
Anyway.
Mm-hmm.
But either way will work. So you can have matrix, I guess written to like a sorted matrix with the position and the.
I wasn't saying sorting the matrix. I was just saying loop through it and store the number and its positioning into like a kind of like a tuple thing, and then sorting that array.
That's the same thing. That's exactly what we're doing.
That's
either way.
That's just a heap, right? The heap does the same thing. It's just cleaner.
Correct.
It's cleaner because you don't have to write all that logic. You just store it into.
I mean, if you can think about it easier in your way, then you should.
No, I'm actually pretty versed in heaps. I've used them quite a bit. In LeetCode anyway, not at work, but yeah. So I know how to use the heap, so I'm good with that. I think Python's is Heap Queue, but the problem is Python is a min heap, so I would have to do a -1 on it to get it to store properly.
Right.
Yeah.
That's absolutely right.
Yeah, that's annoying though, but it's doable.
No, I mean that's fine. You just have to remember to negate the value after you copy.
Yeah, I know. It's just like an extra thing you have to handle. Okay, so I think I don't know if Python do you have to import the heap queue? I think you do, right?
Well, in this interface you don't have to, but normally you would.
So, they already handled it.
So you can just do heap queue dot.
Okay, so I can use
all the heap queue functions are good.
I believe I don't remember the exact same time. I think it's like heap queue dot heap push and heap queue dot heap pop or something like that.
All right, but yeah, that's right.
Okay.
So I don't think you should.
Yeah, I should not name it heap queue.
Because that's
Okay, we're good. All right. So for I in matrix, for j in I. Okay. Oh wait, we want the indexing. So I believe this won't have indexing. So if I do index.
Right. So you want the lengths of these things.
And then I'll call it index j. And Ellie? Wait, no. So in this loop, I will have the element. Oh, I have the index and the element. Okay, so I want to grab the matrix. Wait, so this is in matrix. Index. Then I should name this something else. Oh my god, I'm just gonna name this I. So it's, I can do J. And then
I think there's definitely utility in having good variable names.
Yeah, but then what am I calling it? Like index 2? That sounds bad.
So you can say rows equals matrix or length of matrix, right?
Oh yeah, that's true. That's true. Row.
So before line 6, let's set up rows first.
Okay, row equals len.
It should be rows. The number of rows of the matrix.
Right.
And then columns, right? Okay, this is good. So now you can do for row in range of rows. Right. So this goes from 0 to length of matrix minus 1. This is much more understandable, like what you're trying to do, right?
Okay, so at this point, so these are row and column are both indexes. So okay, so I'll have the index, so I will store it into the heap. Okay, at this, so I will do element equals matrix row col. And then I can just do it times -1 here. Heap queue equals heap queue. Wait, is it heap queue dot heap push, and then I just pass in heap, I think.
So you don't have to redefine heap. Yeah, that's right. Heap push.
Yeah, that's heap push, right?
Yes.
Okay. And then so I push it in. Well, wait, no, I need to push.
You need to push something.
The element, yeah. Oh, it's comma the heap. Yeah. Okay, so we want to push in. Wait, we don't. Wait, no. Yeah, we want the index. That's all we care about.
No. I think heap is the first argument, and then the
is it
value?
Yeah. Okay. So then the index we care about. You just do a tuple. It'll be row col. Okay, yeah, I think that's fine. Let's print out the heap and see how it looks like.
So one issue. Okay, we can do that.
Wait. Oh, oops. Yeah, what's up? What's the issue?
Oh, all of your stuff. The one thing here is that the printed representation of the heap is not the same as when you pop each element out.
Yeah, I understand that. Yeah, it doesn't when you print it, it's not in order.
Right.
I was just seeing.
So if you want the order, you should be printing. You should be doing while length heap. Heap that or heap pop, right? And then
while len heap greater than 0, right? And then just pop it and print it.
Yeah.
Heap queue dot heap pop heap, and just print it. But then this so it did store it. It's just we don't have access to we don't know the key. But then it doesn't matter because as long as it's doing it in the correct way, right? So
well, does this have what you want? Because
it looks wrong. 0 0
right.
0 1.
So you do an element equals something times -1, but you never put it in there. So so where's element?
Oops. Wait. Okay, wait. Yeah, so element is the key. Then the value of the heap. Oh, I see. Okay. So I'm supposed to be passing in. Well, I want the index. So I think it's supposed to be the element. So it's like a tuple of a tuple then. The only issue is how does we need to define the condition for it to insert it, right? Because then if it's a tuple, it doesn't know that that is what you're trying to insert. Like element zero
Well,
should be the element should be like the key of the heap, right? The
sure, but you can do it this way. But I think the making a tuple of the latter two does not need to be done. Like you can just have a 3-element tuple.
oh, you can? Oh, I didn't know that.
You can have
Okay.
n elements.
Okay, I did not know that. Okay, I thought it was just two. Okay, so basically, a tuple is just an array then.
Well, it's a static object that has that many items.
Okay, so okay, yeah, that's fine. It's just like a simpler array then.
It's an array that you cannot change.
Yeah, it's immutable array then. It's a constant array. There you go.
Right.
Okay, all right. So, but how do you know that? I don't remember the syntax to like. How do you tell it that when you're pushing into this heap that you want it to be based on this key right here?
So by default, it will sort by element 1, then 2, then 3.
Oh, if you're passing in the tuple, it'll always check 0 first.
Yes.
Oh, that's guaranteed. Okay, cool.
Well, you can override it by giving it a different.
Yeah, I mean, but default it does that. Okay, let's print it then. Oh, it prints all of it. Okay, cool. -9, -9, 8. Oh yeah, look, it looks sorted, so we're good here. All right, so we don't need this anymore. Okay, so now that we have the heap, so now we want to loop through it for. Oh, I didn't even have to delete that. We could have used that code. So now we want to pop it. So index the roll call equals heap queue that heap pop heap, and then you do can you do like that to store it to these, or you can't do that?
Well, wait. What is?
All right. I'm just gonna store it into an element then.
No, you can do all 3 things, right?
Yeah, that's what I was asking you. Can I do it like that?
Yeah. If you can store it, you can pull it like that.
So it would be element roll call, and you just do that, and it will store it properly.
If there's 3 things to unpack, then you need either one thing that gets all 3 or 3 individual things.
Oh, okay, that's cool. I didn't realize that it can do that. That's cool. I don't. Yeah, does only Python allow this? I don't think any other language allows this stuff.
I guess so. I'm not familiar with the other ones.
I guess it's true. All right, so I have these. Okay, now I'm gonna. So, elements. I mean, technically, I don't even need to flip the negative sign. It's just when I do the checks, I have to check the opposite direction. But to make myself not confused, I'll just multiply by -1. Okay, so now that I flipped it back, now I know my starting index. So now I need the algorithm to jump into that part and start looking all around itself. Okay, so that is the hard part. This is the easy part. Okay, so if I come in here, 0, 0, I want to check right. I want to check up if possible, left if possible, down if possible.
Right. So those neighbors are all defined relative to X and Y or R and C, right?
Would you say R and C? Oh, row and column. Yeah. So. Row.
So you know that all your neighbors, there are exactly 4 possible neighbors.
Yeah. Left equals row -1, I think. Wait, no. Left is that way. Yeah, it is -1. Up equals call +1. No, -1. Down equals call +1. And right equals row +1. Wait, not row. Right. Okay, so I just need to check these. If they're not out of bounds, I just check all of these and see if that element that is next to me is less than me, then this path can be incremented. But then, okay, so here's the thing. How do I handle, so let's say there's multiple paths that I can go.
Mm-hmm.
How am I handling this storage? Like, what am I doing for that?
Right. So as you have the example of the one going to either 2 or 6 or 1, right?
Yeah.
If you go with the 6 first, then your maximum is 3. And if you go with the 2, then your maximum is 4. So you should just you should have like something that keeps track of what their local max is.
What do you mean by local max?
Like from 1, you can go to 2, 1, 6, or 1, right?
1, 2, 6, or yeah. Okay.
So from 2 comma 1.
Yeah, you
that,
can go
that
here. You go to 2 to the left, 6 to the up, and 1 to the
right.
right. Yeah.
So your absolute maximum for that particular location is going to be the maximum across all the paths taken.
Oh, I see what you mean. So you explore all the paths, and then you just store the maximum it can go. So if it's the maximum is always 2, right? It's either 2 or wait, no, the maximum is 1 or 0. Wait, no, because we're starting from the biggest number, right? So
Right.
so the biggest number, if you look around, this one's gonna be 1 because it can't go anywhere.
Mhm.
So then you store 1 here. Well, you don't store into the array, but you have 1.
No, no. You will store 0, 0, colon 1 somewhere. 0,
Yeah,
0.
you have a set that handles that, yeah. And then you move on to this 9. So 9 will check it's the same thing. So 0, 1 is also 1. And then the next index is 8. So 8 here, 8 can't go anywhere either. So it's going to store this as 1 also.
Right.
And then it's going
And
to
then
pop the 6 next. It's probably, I don't know which one's going to pop first, but probably one of these. So 6 is going to go, oh, I can go to 9. So that means it's 2. And then 6, yeah, it's going to check all of it. So 6 can go here, but it can't go here, it can't go here. So the maximum it has is 2 because it has a 2 path, and also has 2 1 paths. So the maximum is 2. So it's going to store 2 for that one, right? And then 6 here can go to 8 or 9. So the maximum between these 2's, it's still 2. So this one's also 2, right?
Correct.
Okay, all right. So I need a structure to store that. So I'm gonna have I guess maybe a dictionary of
Okay.
the tuples of the index and the maximum count. So dictionary what is it called? What I call this? Index? I don't know. Whatever.
You can call it DP or memo, right?
Oh yeah,
You're
this is the
literally
memo. Okay, yeah, that makes perfect sense. Okay.
normalizing what you've seen before.
Okay. So, all right. The algorithm here at this point, it will check. Okay, so if left greater than 0, then I will check if I can go to left. So elements, it would be what is it? Matrix, yeah, matrix, row, matrix left, col. Is it greater than 0? No, it has to be greater than or equal to 0. So I check matrix. No, it's just element. Element is the current number, right? Yeah. If element's greater than this. So if this is bigger than that, it should be if it's less than, right? If it's less than, you can increase. If it's greater than, you don't care about it. Yeah, so if it's less than this, that means you can increment your counter right now. So your max, I guess, max is 0. Max equals max of. We can't use max as a save term. Maximum len, max len. Oh, max len should default to 1 because it should always be 1 at least, I think. So it should be max len equals max of max len. And wait, how am I storing all the other ones? So okay, so I need a separate var for each of these, and then I just check the max at the end. Oh no, not at the end. I can just do it at each point. Okay, so so currently the count should be 1 to start. Oh no, we should pull from the memo first if it's possible.
If it exists.
Yeah, if it exists, then we pull from it and we check. Well, if this condition is true, then we check if this is less. Or no, we just set the max len to the memo and this, and then we store it back to the memo. But if it doesn't exist, it's just 1. So if memo, I think it's just left, right. Can I just pass in a tuple to it?
Well, you should say if left call in memo. Otherwise, it will try to index it, and it won't. If it's not there, then it will throw an error.
Oh, okay. So it would be like left call in memo, and then it'll be memo. No. It's max len equals memo. And max len, I guess. Wait, is that true? Yeah, because max len defaults to 1, and then you try to pull from memo, and then it will store it back in if it's. So yeah, it will set it to the max of between the two, and then just put it back in. So memo left call equals max len. Oh wait, no, this should be outside the if, because if it's not in there, it should put it in anyway.
Oh, why are we setting max memo left call?
Wait, what happened?
Why are we setting memo left call?
Oh yeah, you're right. It shouldn't be left. It should be roll call. Wait. If left. Okay, yeah. So yeah, we're supposed to be storing the length. Yeah, the length of the current one. So roll call. So yeah, we're pulling from. Yeah.
Oh, okay. Now I'm confused.
Okay, what's up?
So when you first process roll call, it will never be in memo. A left call could be in memo.
Yes. Okay, so wait. So you're grabbing from the memo. Left call is. Oh, I see. Left call is the path that you're trying to go to. If it has something there, then you would just.
So if you processed it before, you should find the previous result and then stick your current one onto it, right?
You mean add it?
Yeah. Like basically, let's say you're in the first example, right? You're processing number 6, and you're like, oh, I found 9 before. 9 is 1. So if I am currently at 6, then 6 plus 1. Oh, sorry. Result of 9 is 1.
Yeah.
So I'm just gonna add onto it and be like, oh, I'm at 2, right?
And then you store this index into the memo.
Right.
Okay, yeah,
So zero.
I think I got you.
Oh,
Okay.
sorry, 1, 0 will be 2.
Okay, I think yeah. So you checked if the left is in memo, and then you don't do this. You do max length equals memo left call plus 1, and then you want to check the max of that before you store it back into the thing. Wait, no. Yeah, so no. Yeah, so I think change this one too. Okay, so at this point in the example, if I did 6, and let's just think of left as up. So right here we had 1, so we're checking up, and then we grabbed, there was a memo, it was 1, so this one is less than that, so we increase the current length by 1, and we store this, so we have this max length is 2 now, and then we can store that into the current one.
Right. But I think it's a little hasty to store it into current right now when you
Yeah,
should just
because you have to check
as well.
you have to check the rest, right? I see what you mean. Okay, yeah. So we just keep this. Wait, no. So okay. Oh, shit. So we need more of like we need a more local variable to handle this.
You have that local variable. It's called max length,
Wait,
but somehow you're not calling max on that. So what you erased was correct.
so wait. Yeah,
So
because
you only update it if it's
you only update it if it's greater, right? So it should be this and max length. Right? Yeah, I think that's good. Okay. Then all right, and then now we check the rights and everything. We have to check everything. Okay.
Yeah. But I mean, I feel like you could probably have made this one variable of just like next row, next column or something. But I mean, that's fine.
Wait. Say that again.
So you're listing left, right, up, down.
Mm-hmm.
That means you have to have 4 if statements to check
Yeah.
all of them, right?
Yes.
But if you do something like for neighbor, like let's say neighbor equals, you know,
Oh, you mean
then
like
you
do an array?
yeah,
Okay.
then you just have to check if it's inbound, and then if it's bigger, and then if it's in memo, and then
Oh yeah, I think I see what you're talking about. So instead of doing this,
well you want well not quite. You want XY coordinate. You want row column coordinates.
yeah. So it would be a tuple instead.
You should have 4 tuples.
Yeah, 4 tuples. Yeah. So it would be row minus 1 and column, row plus 1 and column.
Mm-hmm.
And then you got row and column. And then another row and column plus 1. Okay. And then for I and neighbors, if I...
Well, it should be for next row, next column. And
Alright, yeah, to make it more understandable. If next row greater than equals 0 and next columns has to be less than or equal to length of matrix. No, less. It's just less than. So rows is the one that we can't go out of bounds to the left and the right. Oh no, they both have to check that. They both have to check that.
you already defined it in 5 and 6.
Oh, you mean rows and columns, right?
So you want next row is less than rows.
Wait, they should. It has to be less than and not greater than, right?
And wait, yeah, less than exactly, and also greater than equal to 0.
Yeah, for both of them. Yeah,
Okay.
yeah.
So now
Okay.
you know your inbound.
Yeah.
Then you should process.
Now if if element. Well, element, we don't even have element anymore, so we have to. Wait,
you
no,
do
we
have
don't.
element.
No, we have element. Crap. Yeah, my bad. Less than matrix. Next row. Next call. If next. In memo. Max len equals max memo. Next row. What is this? Okay. Does this close properly? No, it does not close properly. You wrap the max. Yeah, this is a max around the tuples. Okay, and then comma max len. Wait, actually, no, I already have the max len. Did I screw up somewhere? No, it should be this. Yeah. Okay. So that will. I will have the max length, the new max length, to store back into the memo. So I want to store that after everything is done. So when this is all done, memo row call equals max length.
Okay.
And I think, yeah. So then this will build me the full memo. And then while I'm building the memo, it should count. Yeah, it should count all the paths. So at the end of this entire thing, I can just loop through the memo and pull out the largest length and just return that.
Right. You could do that, or
Or
you're writing to memo.
Just have a global var checking it now and just store it. Yeah.
Exactly.
So result equals 0, and then I just do it here. Result equals max result and max len. Okay, I think I'm not sure if I have any bugs anywhere. I guess I can test this. So if I do 9, memo's empty, result 0. Wait, do they want? No, 0. It should be 1 because I think the minimum is 1. Okay, so you come in here, 9. Check the heap. So yeah, the heap's already built itself. So this definitely has stuff in here. Pop it. Element is 9 times negative 9 times negative 1 to put it back to 9. Make a local variable of 1. Neighbors is all those possibilities that you can transition. You can check.
Maybe check the input. Can they give you an empty array?
Oh, right. they haven't done that, but I guess we just test it. If they
It
can,
looks like
you can just check.
looks like they
Looks like they can. Is that what you said?
cannot.
Oh. Yeah, it says expected. It says matrix.length is less than or equal to 1. And is less than or equal to 200. So that means it has to have one element? No, it says 1 is less than or equal to m.
Well, they're saying they will not give you an empty array.
Yeah, so you can't have 0 elements, right?
Right.
Right, that's fine.
So then this is fine. You have to return the answer though.
Yeah, I didn't return yet. Return res. Oh yeah, this test case is. Okay, so there's a key error. Memo row column. Oh, that's not the correct syntax. I think it is. Wait. Yeah, it's wrong. It should be this. Okay, that works. This one. That's good. Just put random crap in here. Alright, that looks good. Nice.
Okay, very good. So, I think the key insight here, you have the right idea from the beginning, but optimizing is all about finding, like, I guess, a clever way to make it so that you don't process the same stuff over and over and over.
Yeah, for sure. So I do understand memoization. It's just like if you asked me to do this by myself without you guiding me through it, I definitely could not figure out this algorithm.
I think people have a visceral reaction to like, oh no, it's DP, I don't want to do it.
Yeah,
But
that's
basically,
me. I
all
hate DP.
I mean, all it is you're storing something that you've calculated before, and you're like, okay, and I can look it up, and then
Yeah. I understand the process of it. It's just coding it is like it's just like a completely foreign concept to me.
I mean, it's fine, right? Like the key here was actually not just that. It was more that like if you process it in reverse order.
Oh yeah.
Then,
So that one, like I don't think I would have thought of that. So definitely that was.
well, I mean, you can try not doing that, right? Instead, just try to plop everything out and see if you get like the.
So instead of using the heap and see if it runs properly,
Yeah, you probably will get out.
it won't work for sure, right? Because if you're not doing the heap, it's just if it's just okay. So instead of if you're not like popped, so okay, so
So you would probably have to do something like BFS to or DFS to get.
So basically, like what you're saying is like if you didn't do this, you would basically start from like I guess normal array looping. You would run BFS on everything that it can go through, and then you would memorize the paths that it was going through, right? Basically.
No, you wouldn't even memorize. You would just say like, oh, from this position it was 3, from that position it was 4, from that
Oh, I
position it
see.
was
So
4.
you wouldn't even memorize. You would literally run all the paths through BFS, and then just keep storing a max and just return at the end, right? Basically, and then
Right, so potentially you would have to do like like n squared more calculation or something. Right?
yeah, because you didn't save any of it. So every element in this matrix has to run its whole course, and you don't know anything about it. Is it possible to combine memorize with a DFS?
But there's no need, right? Literally, this gives you the exact order that you care to process stuff in.
Oh yeah, no, this solution is definitely optimized. I was just wondering because like, what if you didn't think to sort it reversely, and that would help you always guarantee the correct answer? How would you handle this otherwise? Would you just
No, then you just get the non-optimal way.
yeah?
You still
So
do it.
so like yeah, if you didn't think of that, your first like let's say you didn't know that, you would just first choice just go like a BFS for this or something. Or?
Yeah. You would do something like BFS. So right now, um, every time you check your neighbor,
Yeah.
it's a O of one lookup. It's basically in the dictionary or it's not in the dictionary. If it's not in the dictionary, then you don't care. That means it's smaller than your current value, right? If it is in the dictionary, it's bigger than your current value and it's nearby, and you
Mm-hmm.
can just look it up what the answer was.
Yeah.
Otherwise, you would have to do up to n squared calculations for each position.
Yeah, because if you didn't pull it from the memorize right here, then it would still have to check
Running it,
everything. But
yeah,
because you
running it.
pulled it out, you already know the count. You're just adding one to it, and like you're done. You're done with the math. So you go to the next step.
Exactly.
Yeah.
Right.
Yeah. So BFS is definitely a lot slower, but
Yeah.
like
Yeah.
in an interview situation, would a BFS be acceptable here?
Maybe like as a first cut, and then they would be like, "Oh, can you make this better?" Or like, "What's the problem when you, let's say, have a grid of, let's say you have one through, uh, let's say you have one through, n squared,
Mm-hmm.
like a snaking fashion,
Yeah.
right? And and every single location has, can have several directions that you can go that are better,
Mm-hmm.
that are increased, right?
Yeah.
How do you do? Like
Yes.
we were,
I mean, yeah, clearly, when you have like billions, like so many elements, it's gonna be super slow because you basically have to run the path. You're probably running the same path like thousands of, or not more thousands, probably like hundreds of thousands of times.
right.
Yeah, so basically, BFS is like kind of like the brute force solution in this scenario.
Yes, exactly.
Okay.
There, it doesn't give you any way to speed it up.
I mean, it's the only like you can't solve it. Like there's no other brute force way to do it besides BFS DFS, right? I think that's the only way you can solve it if you were doing brute force without memorization.
Uh, well, I mean, there's the more advanced algorithms like Dijkstra and stuff, where you start from somewhere and then you find the paths
Oh
from
yeah,
there.
yeah. Okay, I see. Okay.
I mean, I mean, you can see that like with proper like optimizing, then like even BFS is totally fine. Right?
Yeah.
'Cause that's basically what you do. You're checking all the neighbors.
Mm-hmm.
You're not appending to the queue because you already know the answer. Like otherwise, you would append to the queue and then eventually you'll figure out the answer.
Yeah.
Here, you,
That's what I was asking earlier. So you could technically kind of do BFS with the
yes,
memorization,
you
right?
could do BFS, but here you don't have to because the BFS answer is given to you in the memo.
Yeah. Okay. I see. All right. Cool.
Nice.
All right. Thanks.